This meeting is being recorded.
Welcome, and today we're going to be speaking about equilibria. For this lesson, I highly recommend that if you want to participate, you should be using your Microsoft Whiteboard. Okay, so any answer that you want to write it on Microsoft Whiteboard. And then you can share the whiteboard with me, and I would be able to see your answers. Okay, so today we're going to be speaking about equilibria. What is an equilibrium? An equilibrium in the English language is a state of rest or balance due to the equal action of opposing forces. And we can see this equilibrium at the playground when we use the seesaw. So at the seesaw, normally the heavier person, the person that will exert the most force, will be at the bottom, and the person that will exert the least force will end up being on top. Okay? And by changing the position of the body, one can go up and down on the seesaw, changing the equilibrium. In chemistry, this is also true. Okay? In chemistry, some reactions are also going to be in equilibrium. This means that both the forward and the backward reaction are taking place at the same time. Okay? This means that both the backward and the forward reaction are taking place at the same time. And this is a very important concept in chemistry, and we learned to denote it with a particular sign, okay, which we will be discussing later on during this lesson itself. Now, so I would like you to try and write a few reactions on your own, okay? So stop the video and write a few reactions on your own. Once you feel comfortable that you've written your reactions, please come back, join us for the video, and see if those reactions are the ones I've mentioned. If not, you can ask either in the comments below or else ask through email and tell me, are these the reactions that you meant? Okay, but I will be mentioning the two reactions that you would have probably done at O level. Okay, so feel free to stop the video, write the reactions that you think are in equilibrium, and then join us again once you're done. So, normally, the two reactions that are done at O level are the equilibrium reactions for the preparation of ammonia and the chromium, the chromate dichromate equilibrium for the chromium and dichromate. Okay, so this is an acid-base equilibrium, and the other one is an equilibrium that is dependent on the temperature and the pressure. In fact, this here is a sign called the equilibrium sign, and it denotes that the reaction can go both ways, both to the left and to the right. Okay? Now, if you mentioned other reactions, feel free to send them, but normally any reaction that will have this equilibrium sign is an equilibrium reaction. Now, what happens if an external factor, okay, what happens if an external factor changes any of the conditions of the reaction? And I would like you to think about the principle behind what happens when an external factor changes the conditions of the reaction. Okay, again, you can stop the video and write the principle down. Now, the principle is Le Chatelier's principle, and it states that if a dynamic equilibrium is disturbed by changing the conditions, the position of the equilibrium moves to counteract the change. For example, we can change temperature, concentration, and pressure. If we change any of these three conditions, the reaction will counteract our change by opposing us, okay? And it will, if we increase the temperature, the reaction will want to decrease the temperature. If we increase the concentration, the reaction will want to decrease the concentration. If we increase the pressure, the reaction will want to decrease the pressure. So let's see an example of this using ammonia. But prior to that, we are going to watch a short video on Le Chatelier's principle.
In this lesson, you will learn about Le Chatelier's principle, which explains what a system at equilibrium does in response to stresses. Let's return to our original example of you digging a hole and your friend refilling it simultaneously. If you start digging at a rate faster than refilling, the hole gets larger. In order to maintain a constant size of the hole, your friend must work harder to fill it faster. Following on the same idea, when a chemical system at equilibrium is stressed, the system works to restore equilibrium. This is Le Chatelier's principle. The stresses are changes to the concentration of either the reactants or products, changes to the pressure, although this is only applicable to gaseous systems, changes to the temperature. Let's examine a hypothetical reversible reaction at equilibrium where reactant A reacts with reactant B to form product C and product D. If we added more A and B, the system becomes stressed and is no longer at equilibrium. To counteract the stress, the system forms more C and D in order to remove the excess A and B. The equilibrium, therefore, shifts to the right. If we added more C and D, the system becomes stressed and is also no longer at equilibrium. So to counteract the stress, the system forms more A and B. Therefore, the equilibrium shifts to the left. What happens if we remove C and D as they are being produced, or if the concentration of C and D is decreased? Please pause the lesson to think about this and resume when you are done. The system is now stressed and no longer at equilibrium. To counteract the stress, more C and D are produced, so equilibrium shifts to the right. When concentration increases, equilibrium shifts to the opposite side of the reaction. When concentration decreases, equilibrium shifts to the same side of the reaction. Changes in pressure. The stress to a system at equilibrium is only applicable to gaseous systems. For this stress, we will examine another hypothetical reaction at equilibrium, where reactant A reacts with 2 moles of reactant B to form product C and product D. An increase in pressure means that there is a decrease in volume, so there is less space. Equilibrium will shift to the side of the reaction with fewer moles. In our example, an increase in pressure will cause equilibrium to shift to the right, since there are fewer moles, 2 moles compared to 3 moles on the left. A decrease in pressure means that there is an increase in volume, so there is more space. Equilibrium shifts to the side with more moles. So in our example, equilibrium shifts to the left. So an increase in pressure favors the side with fewer moles, and a decrease in pressure favors the side with more moles. In our next lesson, you will learn about how a system works to restore equilibrium in response to changes in temperature. In summary, Le Chatelier's principle states that when a system at equilibrium is stressed, the system works to restore equilibrium.
So, after this video is done, then we are going to go back and discuss the equilibrium of the reactants.
In this lesson, you will learn about how a system at equilibrium responds.
Okay, so we will be discussing how ammonia Okay, the equilibrium of ammonia is changed when we change the pressure and the temperature. Actually, how do you think the equilibrium will change? What do you think will happen to a reaction at equilibrium when we change the pressure and the temperature? Okay, so stop the lesson here and answer those two questions. What will happen if the pressure is increased? And what happens if the temperature is increased? Okay, and come back when you're ready. Okay, come back when you're ready. So, what happens if the pressure is increased? Therefore, pressure increases. Therefore, reaction will want to decrease pressure. There are less moles on the right. Therefore, reaction shifts to form an H3. Okay? So if the pressure is increased, reaction shifts to the right, increasing the yield. Okay? So the yield will increase. Okay? Reaction shifts to form more ammonia. What happens if the temperature is increased? So we can see that this temperature here, this reaction is exothermic. Okay? So the forward reaction, by the forward reaction we mean formation of ammonia, it is exothermic. Okay, so let's move this downwards a little bit more space. So if the temperature is increased, therefore reaction will want to decrease temperature. Okay? Endothermic reaction is the reaction to the left. Therefore, reaction will form the reactants. Okay, so when we increase the temperature, since the forward reaction is exothermic, then the backward reaction would be endothermic. Which means that in order to decrease the temperature, then it is very important to shift the reaction to the left, to react to forming nitrogen and hydrogen. Okay? Now, there is another topic here that we can discuss, which is compromise conditions. Okay? Instead of discussing it in equilibria, we will be doing it in rates of reactions. Okay? But the conditions for this reaction are temperature of 450 degrees Celsius and pressure of 200 atmospheres. We can say that the pressure is high, as expected through Le Chatelier's principle. So the higher the pressure, the more product will be formed. But the temperature is very high. Okay? And we'd expect that a higher temperature will shift the reaction to the left. But what would you rather have? 1 cent per minute or 10 euros per day? Okay? 1 cent per minute or 12 euros per day. And the answer, most probably for most of you, will be the 1 cent per minute, as it will amount to more. And in fact, increasing the temperature, okay? Increasing temperature increases the rate, which means that the product is formed faster. Okay? And if the product is formed faster, even if the yield is lower, okay, overall, there will be a lot more product that is obtained. Okay? Overall, there will be a lot more product than is obtained. Now, a quick question connecting what we're doing today in the Chatelier's principle and equilibria to what we had done in Gibbs free energy. So let's write the reaction again. Is this reaction always spontaneous? Is this reaction always spontaneous? So stop the video here. I will be explaining the answer shortly. Okay, stop the video here and think about whether this reaction is always spontaneous or not. If not, advise when this reaction will be spontaneous. So Gibbs free energy is delta G equals delta H minus T delta S. Okay, now in this example, delta H is negative and delta S is also negative. Why? Because there are 4 moles of gas on the left and 2 moles of gas on the right. Therefore, amount of disorder decreases, which means that we will have a negative delta S or a negative entropy. Now, at this point, we will know that for delta G to be negative, okay, delta H must be bigger than the delta S. Okay, for delta G to be negative, delta H must be bigger than T delta S. And in fact, since the reaction is at equilibrium, that means that for this reaction at the conditions used, delta G is approximately 0. We say that as delta G approaches 0, as discussed in the previous chapter, okay, then we will be having an equilibrium reaction. To close off today's lesson, I would like to speak a little bit about the equilibrium constant. So this is a constant associated with equilibria. And for any reaction at a given temperature, there will be a respective ratio of products to reactants. And this is in fact, okay, and this is in fact a constant, okay? So it's a constant of equilibrium. So let's use, okay, ammonia, or because ammonia is one of the examples. Let's use ammonia because I think it's one of the easier ones. Or let's use, in this case, dissociation of PCl5, okay, gaseous to give PCl3 gaseous plus Cl2 gaseous. Okay, so it's an example where we need to find the constant. So what is the constant? The constant is the ratio of the product. So we'll say Kc is equal to concentration of products over concentration of reactants. And here, the products are concentration of PCl3 times concentration of Cl2 over concentration of PCl5. Okay? So please note, the products are multiplied together. Okay? The products are multiplied together. Okay? And in fact, we're going to work the first example together. Okay? Since the products are multiplied together, any numbers, okay, showing the number of moles of reactant or products will be written as a superscript in the reaction, okay, as a power. But we'll write an example. Today, we will not be discussing how to write the units. We will leave the units for next lesson. Today, we're just going to be discussing how to write Kc. Okay? We will be leaving the units out of it. Next lesson, okay, we will revise the equilibrium constant, how to write an equilibrium constant, but then we will also include how to write the units of the equilibrium constant. Because the units of the equilibrium constant will change depending on the reaction. So let's do one together, okay? And then I will give you some time for you to work all of the others out, okay? To pause the video and work all the other questions, and then we can work them all out together here, okay? So Kc is equal to product, which is N2O4, over the reactants. The product is N2O4, as we can see. Then you have the reactant being NO2, with the coefficient being 2. Therefore, the power will be to the power of 2. Okay? So try and work the next 4 on your own. And then we will come back and work these out together. Okay? And I will show the working for all of the rest of the questions. Okay? So feel free to pause the video here, and when you're comfortable with your answers, join us again. Okay? So for the first one, 2, I will not be writing the equations. Well, I will write the equations for these. So I wrote ester instead of the full ester because of space, okay? So here, Kc is equal to concentration of ester times concentration of water over the carboxylic acid, okay? Propanoic acid times the ethanol or the alcohol. And again, we can see products over reactants, okay? And this will always be the case, where it will be products over reactants. 3, we have hydrogen gas plus iodine gas to give 2Hi gas. And we will have here again, Kc is equal to concentration of products. There are 2 Hi, so therefore it will be to the power of 2 over H2 times I2. Okay, so it's products. I'm including the power there over the reactants. Okay. 4, where we have 2SO2 plus O2 to give 2SO3. Okay, so this will be Kc is equal to SO3 to the power of 2 over SO2 to the power of 2 times oxygen. Okay, so SO3, the 2 is the power there. Then you have oxygen and SO2, which are these ones here. And you have the power, the 2 for the SO2, which is the power over there. And the last one is N2 plus 3H2 to give 2NH3, okay? and you will have Kc is equal to NH3 squared over N2 times H2 cubed. And again, NH3, we have the square because we have two NH3s. Okay, then we have H2 and then 2, and we have the cubed because we have the 3H2. So let's revise what we've done today. And if you want to work more examples, please go to the workbook, to the chapter of Equilibria, and work exercises 1 and 2. Okay? So first we started off with what an equilibrium is. So equilibrium is a state of rest or balance due to the equal action of stopping forces, of opposing forces, apologies. Then from there we discussed that equilibria can also happen in chemical reactions, where the rate of the forward reaction is equal to the rate of the backward reaction, where we then discussed Le Chatelier's principle, okay? And we said that Le Chatelier's principle can be used to determine how external factors will change the yield or the equilibrium of the reaction. And we combine this with a chapter that we'll be doing in the future, rates. Okay, so we will be revising what we've done today. Today we've spent literally no time on it, okay? So we'll be seeing this in a lot more detail in the future. And we also use this to revert back to what we've done in our last lesson, Gibbs free energy, where we have spoken that this reaction, it will not always be spontaneous, and it will only be spontaneous when delta H is bigger than T delta S, because that would make delta G negative. We finished the lesson by introducing the equilibrium constants. We finished this lesson by introducing the equilibrium constants, and we will be using these pretty much in the next 3 to 4 weeks, where we'll be using different equilibrium constants, but all the equilibrium constants are going to be products over reactants. And this constant is the relationship between the amount of products and reactants at any given temperature. So the equilibrium constant is going to be determined, or is going to show how much product we're going to get and how much reactant we're going to get. And this will be a ratio. So I will see you in our next video, where we will be speaking about equilibrium constants, and we will be seeing how to write the units for Kc and how to use Kc to find the concentrations, okay, for different reactions when you add specific amounts of reactants, okay? But that will be for the next lesson. Hope you enjoyed this lesson and have a good day. Thank you.